Okay, great. Welcome everyone. I apologize, we're a little bit late on the start of our webinar. We're allowing some people to log in. So welcome, Touch Current Testing 102. So this is going to build on our last webinar, Touch Current Testing 101, which Syed Abidi presented. Speaking of Syed, he'll be our panelist today. He is our most experienced application engineer here at AR. So he has built and helped customers set up a multitude of touch current testing systems. So if you have any questions, feel free to reach out to him through the chat box. Our organizer today will be Allison Oba. She does magic every time we have a webinar. So if you have any issues hearing me or seeing me, this has actually been an issue our last two webinars where my sound has cut out for about 30 to 60 seconds. So we might have someone interrupting me just to let me know, hey, go back. Let's make sure everyone gets all the information they're here for. Again, if you have a question, use our Q&A utility. This webinar, along with all our past webinars, will be recorded and they'll be available for you through our website, through YouTube, or just feel free to reach out to Allison and she can send you a copy of this one. So let's quickly recap our previous webinar. We talked about shock hazards, why we test for touch current, what's the point of it? Obviously looking for shock hazards, how that specific current affects the human body, and what human body impedance is, how it's measured, how certain measuring devices are created to simulate that impedance. Next we talked about a bunch of different leakage currents, what is touch current, and Syed gave some examples of what those were. But as far as today, our learning objectives for today, we're going to specifically delve into the definitions of what each of these leakage current types are. We're going to then get into a description, talk about the networks and the measuring devices, and then we're going to, when you're talking about the topic of touch current or leakage current in general, it's hard not to get kind of steered towards IEC 60601-1. So we're going to look at that standard, talk about some specifics, diagrams, and get some videos on it. So let's get started with our content. So leakage current types. First we have touch current, which is also known as enclosure leakage current. It's electric current through a human body when it touches one or more accessible parts of an installation or surface of electrical equipment. So again, touch current, also known as enclosure leakage current. Now, you can see we don't have earth leakage. I recall from past webinars we would have a poll question, what's the most, or which leakage current type test are you running? Earth leakage was by far the most popular. Everyone does earth leakage, you need to do it. But today we're going to focus on these four: touch current, patient leakage current, which is current flowing from the patient connections via the patient to earth. So I've come in contact between patient connection on a medical device, and that current is flowing back to earth through me. We have patient auxiliary current, which is current flowing in the patient in normal use between any patient connections and all other patient connections. So two patient connections. We're testing the insulation between those two. And finally, probably the type of testing that is we get the most questions on. It's probably the most complicated application of mains voltage on an applied part or patient lead. So patient lead types. You guys are probably familiar with these terms, and let's discuss some in a little bit of detail. So B-type. B-type, to qualify for B-type, it's probably the least stringent as to what you have to pass. Now, B-type is an applied part that provides protection against electrical shock. That's a pretty basic definition. The standard specifically would call B-type is an applied part complying with the specified requirements of this standard to provide protection against electrical shock, particularly regarding allowable leakage current, and marked with symbol 1 from table D2. We'll get into that. But it's pretty much your basic applied part which provides protection against shock. Now F-type is like a floating B-type. So you can have that F stand for floating. It's an applied part in which the patient connections are isolated from other parts of the medical electrical equipment. So that's what ME stands for. Now below the F-type we get into more specific BF and CF. BF is your applied part which provides a higher degree of protection against electrical shock than that provided by your normal standard B types. Now when we get to CF, that's the most protection. That provides the highest degree of protection against electric shock than that provided by your BF, F, or B type. More specifically, I kind of wanted to give the standard definition, and when I say standard, of the 60601-1 standard. So a CF applied part is complying with the specified requirements of this standard to provide a higher degree of protection against electrical shock than that provided by the BF. Now, this is tested with fault conditions. Now, those fault conditions that we're going to, I believe, before I move on to that, we'll talk about fault conditions. We're going to specifically look at diagrams outline each fault condition and what is happening to your device. So how is it measured? We have an MD, or a measuring device. Leakage current is measured through a human body impedance network, also known as a measuring device. So these measuring devices are specifically designed to simulate a human body's impedance, okay, through various conditions. These networks are usually built with resistors, capacitors, and why have so many? Well, we need them to react differently, a different frequency curve, because all our bodies act differently. So depending on the product you're testing, each standard will call out for its specific measuring device. Now, I was referring to the normal and single fault conditions. These are measurements taken under normal conditions for normal, so that just means I plug in my medical device, run it, how much leakage do I see? How much patient leakage, how much enclosure leakage, earth leakage, auxiliary leakage. Those are your normal conditions, which we don't expect a lot of current leaking because obviously we can't have it going to the person connected to the medical device. And under fault conditions, measurements are also taken under single fault conditions to simulate worst case scenarios. So we're going to look at some tables in the next couple slides which give us our thresholds for what is allowable under these single fault conditions. And so the main question to ask is, what is the severity of electric current someone would be exposed to if they were to touch the DUT under such conditions, right? That's the whole point of the standard and these measuring devices. Is we want to identify what's the worst case scenario. If I am in a hospital and I'm connected to one of your products, you can have peace of mind that no more than X amount of microamps are going to pass through my body or are leaking onto the surface of your product. So a little bit more on how it's measured. So these are the MDs for specific standards. So these screenshots are actually taken from our Omnia 2 model, our Omnia 2 series. These are all the MDs that come with the Omnia. These are probably the most tested standards, which is why we supply these these measuring devices. We have IT equipment, electric spas, medical devices, usually hospital beds. Those type of things are what this testing is geared towards. We also have an external option. I don't know if you could see that. So if your product is a little bit more of a niche market and you don't see your measuring device already pre-installed in our Omnia, you can create easily. We have a pull-out PCB that you can create your specific measuring device and test it through our Omnia. So here's a diagram that we have. We're going to actually see the real thing on our video, but just let's go over what our connections mean here so we kind of have a brief background of what we're going to be looking at. So this is our adapter box, right? It comes with all our instruments. It has 3 connections. We have our line, our neutral, and our ground. So this adapter box is going to power up our product, our DUT. This will provide the line input to your DUT with an internal source that's in the Omnia. Now, depending on what type of product you have, the standard calls out that you should be testing to 110% of that rated voltage. So, for example, if your product is made for use in the US, you'll be testing on 132 volts, which the power source inside the Omnia can provide. And it will be supplying it through this adapter box. Now this adapter box has access to line, neutral, and ground. So on top of providing input power, we also have access to those lines so we can simulate, or not simulate, but actually provide those fault conditions. We'll open neutral, we'll open ground, we'll reverse polarity through our instrument, and those fault conditions can be achieved. Now, if you were doing your earth leakage, you would have this ground connection here, or this chassis connection onto your DUT, and that's where the current will return to our instrument. But more specifically, I want to look at these 2 connections, our probe high and probe low. And so let's see if we can go back here. You can see this A and B on our measuring devices. Those are the 2 sides of your measuring devices, and that's what we call probe high and probe low. So you have the ability to attach both sides of the measuring device to whatever desired locations you'd like, depending on what type of test you're running. If you're running touch current, which we'll do in a second on a video, we'll show you how those connections are made. But before we get too deep into that, let's talk about what's actually happening with the leakage current. So you can see on the left side of our screen, this is considered our Omnia tester, okay? And the right side is your medical device, your DUT device under test. During normal conditions, now this green line, I don't want you to think it represents your normal line neutral power, because obviously we would have this neutral highlighted green if that's what I meant, but what it's specifically showing you is the leakage current. So I have line and neutral. Let's assume this is connected to our adapter box here. So now my DUT is powered up. Line and neutral is supplying it with its input 132 volts, let's say. Now if there were any leakage current, what would happen to it? Well, ground would catch that, right? So ground would catch that. It would bypass the MD, so the MD would probably read close to 0 amps, and it would return back to the source. That's normal conditions. That's how you want your product to work. That's why we have a ground circuit, right? It's a safety measure. Now, let's say neutral was open. If neutral was open, I'd expect your product to probably turn off, right? You've opened the loop. There's no way for current to travel through your device. But that fault condition, what happens? Does my leakage current increase? Does my touch current increase? So that's something that our measuring device would give us that value, but ground is still closed. So regardless, ground is still shorting out the MD. Okay, now we have reverse polarity. So now we reverse polarity. What does that do to our touch current? Does that increase it? What type of adverse effect does that have? But again, unless ground is open, we're shorting out our MD. So going on a lot of client visits, I notice a lot of people don't run the test with the ground closed condition because logically you're just going to get close to 0 amps, 0 microamps, 0 milliamps. Now when ground is open, that fault current has nowhere else to go but to your DUT, which will now make its way back through the MD where we can make proper measurements of what that current is. All right, so I hope that kind of gives us a clear background of what these fault conditions are, what they do, and now that I'm putting myself in the position, I probably still would run the test with ground closed because the more data we get, the more better on how our products behave. So, as I said, if you're talking about leakage current, you can't help but be steered towards the 60601-1 medical equipment standard. So let's talk about the requirements for leakage current and patient auxiliary current tests. Our requirement is to test in normal conditions, which we talked about, and single fault conditions. And another thing you can do, a lot of our clients do double fault conditions. What happens when our polarity is reversed and our neutral is opened at the same time? Like I said, the more data you can get, the more you can identify the characteristics of your product and how it behaves, the better you are to make a decision if you need a redesign or if you have peace of mind that it's safe, regardless of what fault conditions occur, how many, in what combination. You have peace of mind that, hey, that current is below the limit required by the standard, and I feel confident connecting a consumer to that product. Now, it's also tested with 110% of the highest rated mains voltage. I noticed looking through the standard, that can vary depending on, I believe if you're running a motor, I believe it's 115 to 120%. So it's really important to get down to the nuance of the standard to make sure you're properly testing to the requirements. And obviously you will be testing to your rated supply frequency. So the past criteria, earth leakage, which through past poll questions we've learned almost 100% of people are doing earth leakage. And those limits aren't too stringent. Less than or equal to 5 milliamps under normal conditions, which is what the NC stands for, or 10 milliamps to single fault conditions. Now, you can see the drastic change between touch current and earth leakage current, because touch current, I'm guaranteeing that it's probably going to hit the consumer or the patient. So those limits are less or equal to 100 microamps normal or 500 microamps single fault conditions. And those patient leakage current thresholds or high-low limits, well, you need to refer to table 3 and 4 of the standard to identify those exact numbers. I have those tables in the preceding slides. We'll get to those soon. Now, within leakage current, we're going to talk about, we've talked about earth leakage, which Saya did a good job covering on testing, touch current testing 101. But what we're going to delve into a little bit deeper with this webinar is our patient leakage. So patient leakage to earth, patient mains and applied parts for F-type patient leads, mains on signal I/O ports or patient auxiliary leakage, and mains on non-protectively earthed chassis point. We might not be able to have enough time to get to all of them, but we'll do our best. And whatever we do cover, I want to make sure we get. Where I'm actually we're gonna have a poll question, pop quiz. So we'll see if what I'm explaining is kind of making sense. So here's that table 3 I was referring to in the last slide. Allowable values of patient leakage currents and patient auxiliary currents under normal and single fault conditions. So you can see here under, depending on what type of CF applied part, BF, or B, you know, a B AC/DC. Now, something to note, a lot of testers don't give you filters to just measure AC or just measure DC. They usually just give you total leakage. So for the total leakage, you're going to want to probably set your limits to the AC leakage. Now our Omnia actually does give you those filters, so if you're only preoccupied with the DC or the AC, you can choose those specific filters and you'll only get those specific values. But going back to the point I was trying to make, you can see the thresholds are completely different. A CF, under normal conditions, you're allowed 10 microamps, which, I mean, even the resolution on most testers might not even be able to get you that, but our Omnia, of course, can. And 50 microamps under single fault conditions, where a type B, which is, like I said, your most common or most lax restrictions, you get up to 500 microamps to 100 microamps. And you can kind of see that trend when we're talking about patient leakage and total patient leakage. You know, going from type B to type CF, those limits become very limited. Now, table 4, allowable values of continuous leakage and patient auxiliary currents. So this is for patient auxiliary. We have our earth leakage, which we talked about, most people do. We have patient leakage current. So again, you can kind of see that trend here. With normal conditions, your thresholds are a lot lower than under single fault conditions. So what's this mean, right? What's this mean? How do you use these numbers? How can you utilize this information? So this figure 14 was taken from the standard, all right? This figure 14 is designed to explain how you should be testing for touch current or enclosure leakage, which is another term for it. All right, now I give credit to compliance engineers if they can read this diagram and set up your test without asking any questions, because there's a lot of stuff going on here, and that's why we provide these webinars, because we want to make sure all these details are clear. So let's look at T1 here. So what's T1? That's my transformer 1, or that's the mains that are providing power to my DUT. So if I can get my scroller here back up, here's my mains, right, my high side and low side of my transformer 1, and if we follow that, that's headed towards my DUT. So here's your product, here's your medical device. And similar to the circuits that we saw on the Omnia screenshots, this is where we derive them from, this is where we take them from. So you can see with these switches S5, we're reversing polarity. You can see with S1 here, we're opening neutral or the low side of our transformer 1. S7, you can see our protective earth, so we're opening up our ground circuit. And just like we spoke about in the past diagrams, if this protective earth circuit is closed, what am I doing? I'm shorting out my MD. I'm bypassing my MD, and all leakage current is returning to the source, and I should be expecting close to 0 amps leakage on my reading. So this is where we get to the important part. So let's assume ground is open right? So here's my MD. What's my MD attached to right here for touch current? I see my MD, one side of my MD is connected to a reference point from the transformer, the low end, and the other side is to just the surface of my DUT, the surface of my medical device. Meaning this MD is simulating my hand on the surface of that MD, hence touch current. Okay, I have another MD over here. I have it between two touch points on the medical device. So you might need to run that test as well. So that's touch current. We kind of understand that. I have my transformer here that's powering up my MD, ideally at 110%, not ideally, I mean, it's in the standard, 110% of your rated voltage at its rated frequency. So my product, it's got juice now, right? It's getting juice. I'm going through all these fault conditions, normal polarity, reverse polarity, neutral open, neutral closed, ground open, ground closed, ground open. Now my MD is seeing leakage that's on the surface of the chassis of my DUT, going through the medical device. My Omni is reading that, it's displaying that, it's telling me how much leakage I'm getting. Hopefully it's under the limit on the standard, and that current is returning back to the source. All right, that makes sense, right? So that's touch current. So now let's look at patient leakage. Very similar. I don't know if anyone can identify the only difference here. We still have, well, besides it's in French apparently, we still have my input power. I still have my reverse polarity. I still have my protective earth switch, and I still have my MD with one side referenced to the low side of my input power, or T1, but the other side is now contacting a patient part on your medical device. So this might be, you know, I don't know, a heart rate monitor or something that goes onto the body when you're, you know, in the hospital. I'm lucky to be ignorant that I can't think of parts at a hospital that go on you, because I don't have that experience. But it's some sort of cardiac monitor, right? I want to know how much is leaking from my input power to that heart rate monitor that's going to pass through me and return to ground. So this next slide should be a video. Okay. I asked for some patience on these videos. I've been having trouble having them play cleanly, but actually that reminds me, let me turn off my camera, because that usually helps in having these videos play cleanly. Let me check our chats, make sure no one's, okay, everyone can hear me. Camera's off. Let's go back to our video here. So this was like that that diagram we saw earlier, right? I have my line neutral. This is attached to an adapter box where my device under test is plugged into. That's where I'll be getting my 132 volts. Here is my ground connection. Here is my probe high and probe low. So what test am I running right now? I said I'm going to run touch current, right? So like we saw in that diagram, one side, these are the both sides of my medical device. One side of my medical device is to the low side of my input power. Now that will be done through this adapter box. And the other side is on a touch point of my DUT, right? So although I have something connected into both of these, I'm only using one right now. And how do I tell my Omnia to do that? It's by the probe configurations while I'm setting up my test. So fingers crossed this plays a little bit smoother than it did. Let me mute that. So again, you can see my connections. My DUT is connected to the adapter box where it's getting its input power. And now what I've done to my medical device is attach foil around it because I want to give it a conductive surface. I want that current to be able to flow back to my probe, to my measuring device. All right, so that those connections are pretty self-explanatory, right? Again, I have one side of my measuring device on a touch point of my DUT and the other side referenced to the input power of my T1. So let's go to the front panel of my Omnia 2 here. So the first thing I'm going to want to do is verify I have input power. The great thing about this Omnia 2 is it has an internal source. So I don't need to buy a second source because you can't plug in your DUT into the wall because that's going to give you what, 115, 120 volts. I need to be at 132 volts, and I need to be confident that I'm truly getting 132 volts. So I'm going to go in here into my setup system screen, okay, hardware, and just verify that my AC source is on. So that's on. Activating that gives you extra parameters when you're setting up your line leakage tests. So now we'll set up a test. You can see we have two LLT tests set up here. What I want to do is have one be in normal conditions, meaning my polarity will not be reversed, my neutral switch will be closed, and my ground switch will be closed. All right, let's verify that, edit that. Okay, so this leakage high number here, this is where those tables come into play. Whatever type, whether type B or whatever type of applied part connection I'm testing, that's my high limit. That's what I'll put there, whether it's 100 microamps, 50 microamps, or if I'm doing earth leakage, what did I say, 5 milliamps, right? You can get up to. So that'll be my leak high number. That's where that table comes into play. You plug that number in here. This volt high, volt low, a lot of people get confused that this is what I'm setting my source to. No, this is what you're setting your limits. So we probably ran this at 120, just for our all intents and purposes. We'll just leave it at 120, even though they should be ran at 132. So if it was ran at 132, I'd set my volt high at 136, maybe my volt low at 128. But for our purposes, we could leave this at 0 and 125. Our dwell time is how long I'm going to be recording that leakage. So how long the test is actually ran. And this delay time, this is actually a very functional feature, because a lot of your medical products don't instantaneously power up, right? It goes through processes. It needs time to activate certain circuits or certain parts of that medical device. So if it takes 30 seconds for your DUT or your product to get into its steady state or its normal use current how it runs, then add 30 seconds to your delay time, and we won't start making measurements until that time has passed. And now using these soft keys, here are our fault conditions. Neutral's closed, reverse off, ground closed. So ground closed. So what did I say about that earlier? Once ground is closed, I'm pretty much bypassing my measuring device. So I should expect close to zero leakage. Let's let this run a little bit further. Let's look at our measuring devices. So we're going to use 60601-1. Here you can, it shows you the specific system, measuring system here. I have a 1 kilo ohm resistor with a 10 kilo ohm resistor and a capacitor, right? This is designed to simulate human body impedance. And if you test to a different standard, just it's easy as scrolling through these, selecting the correct one, and the Omnia will do the rest. So let's keep playing this. Now this is probably one of the most important parts when you're setting up your test, your probe configurations. Now all of you do earth leakage, right? Protective conductor current. So you'd be set to ground to line, where none of your probes are being used. All measurements are made internally because that adapter box has access to ground, it has access to line, so all those measurements can be taken internally of the Omnium. I don't need an external connection to your DUT. Now we're doing touch current though, so I do need one side of my MD to be attached to a touch point on that DUT. So you can see this red switch right here. It's now switched to probe high, and this probe high will be connected to the touch point, which we saw on the foil. And probe low is still connected to the low side of your input power, as we saw in the diagrams from the standard. So let's continue this video, and you can see as I flip through, those switches are opening and closing depending on what we want. So we want probe high to line. That's set. Let's go to more. Our AC source, we'll leave it at 120 for now. If you're running a real test, I'd put it at 132. Change your high and low limits accordingly. Now, something I didn't go into is the step 2. The only thing I changed was I opened ground, because I want you guys to be able to see the difference in current when that fault condition is activated. Okay. Let's go ahead and run this test. Perform test. I'm going to hit this green test button. Now, something else before I hit this button to remember is a lot of your DUTs, a lot of your medical devices, they have an on switch. So it's a simple thing, but even myself, you forget. I hit test, oh shoot, I have to turn on the device. You know, I have to press this on button. We can see right now it's pretty much zero leakage with these conditions. Neutral's closed, reverse is not on, and ground is closed, right? 0.1 microamps, very little leakage. And now I'll turn on the medical device. That was in my hand. I do not paint my nails. So even with it on, 0.1 microamps. So it passes that because it didn't get anywhere near. What does it mean it passed? It means it didn't get anywhere near supplanting or surpassing our high limit, which was at 1,000 microamps. Oh, microamps, I'm sorry. So now let's see what happens with ground open. You can see an immediate rise in our leakage because that MD is no longer being bypassed. So we saw 25 microamps, which in itself still isn't a lot of current. And I mean, think about it. So there's 25 microamps on the surface of that medical device that I have foil on. I mean, it's not enough for me to feel a tingle or perceive in general, but with sensitive instruments connected to me, who knows what those 25 microamps or 50 or 100 microamps can do to those instruments or to, you know, my heart rate. So that's why it's important to keep that current low. So before I continue that video, I kind of wanted to do a poll question. Let's see how we're doing on understanding what's going on here. I just did touch current, correct? So now, what modifications need to be done to our current setup to turn this from a touch current to a patient leakage test? So I'll let Allison open up this poll questions. You should be able to see your answers. Do I add a second transformer, otherwise known as T2? Do I change probe settings from probe high to probe low? Disconnect my probe high from the foil and connect to a patient connection? Or is it none of the above? Is it none of those? Do I need to do something different to make this into a patient leakage test? So we'll give you guys some time to answer that. We appreciate the feedback to see how we're doing and properly teaching you what needs to be done to perform these tests. Let me grab a pencil here so I can write down these results and see how clear The earlier part of our webinar was to explain what needs to be done or what in the diagram needs to happen to turn this from a touch current test to a patient leakage test.
Hi all, I'm going to go ahead and close the poll. Thank you all for participating. Again, we asked what modifications need to be made to our current setup to change this from a touch current test into a patient leakage test. 0% of people said to add a second transformer. 15% of people said to change the probe setting to probe high, probe low. And then 85% of people said disconnect probe high from the foil and connect it to the patient connection, which is really great. That's the correct answer. Way to go, guys. But Anthony, I think it might be a great idea to just quickly go over why C was the optimal choice and why answer B might not be the best. Again, thank you all.
Okay, yeah, Allison, I absolutely agree with you. Those results are awesome. There is no curve in this class, which I always depended on. Okay, so let's go back to touch current and compare it to patient leakage. Again, the only difference we have is my probe high side of, probe high to line. Yes, my probe high side of the measuring device is no longer touching my device, but is now connected to that applied patient part. Okay, so this is why there's no need to change from probe high to probe low, because one side of my measuring device is still referenced to the low side of my DUT input. The only thing that's changed is the location of our probe high from a touch point to a patient applied part. Okay, so let's go back to our video and see our difference in values from that. So I'm going to go ahead, reset the test, and I'm going to disconnect from our touch point and connect to my applied part. Now, I would recommend, which most of our clients do, is they make custom cables. You know, instead of having a clip, actually have the connector that goes into there just to get more precise readings or measurements. But for our purposes, our alligator clip suffices. Okay, now that everyone's dizzy, let's go back to our perform test. Remember, our first, there are no fault conditions here. We'll turn this back on. Again, same reading, right? Close to zero leakage. Now, we go to the second part where our ground is open. We get a little bit more leakage, about 0.6 microamps, which is still well below what our limits are. So this no-name medical device did a great job going through these tests. We never saw more than 25 microamps, which is well below the limits it needs to stay under. So awesome, great job on the poll question. Great job. Let's see. All right, so now patient auxiliary. So now we do see some changes here, right, on this diagram. So these diagrams are taken directly from the standard. Let me make sure everyone can hear me and see me. I know sometimes when I go back and forth from different applications, people will lose out. Let's see. I'm all good, doing great. Thanks, Allison. So, okay, what were we doing in patient leakage? One side of the MD to reference to our input power, the other side to whatever I'm trying to test. Am I trying to test a touch point, or am I trying to test a patient leakage point, right? But now we go to patient auxiliary current. my MD has disappeared. Oh, nope, it's on this side now. So patient auxiliary current is testing the barriers between two patient connectors. It can be your signal in, signal out. It can be, like we said, two different connections on your body. But now we're no longer referencing our input power. So that 15% of you that answered the poll question, probe high, probe low, you got a little ahead of yourselves. You were probably thinking of patient auxiliary current, because both sides of our MD now are on an external point. So now we are going to need to be on probe high, probe low. But we still have our same fault conditions: reverse polarity, open ground, open neutral. So let's play this video. I ask for a little bit of patience when I pull up this video, because they seem to play best in QuickTime, and QuickTime does not like me. Awesome. So don't mind our intern's feet here. We have probe high and probe low connected, right? Let's see where we have those connected. Let me mute this actually. So our DUT is still connected to our adapter box because I need input power. I still need to get those 132 volts to my DUT to test that worst case scenario. So one of my probe highs is on a patient connection on the back, while my probe low is now on that same patient connection I had on the front. So you can see now we're testing on two external points. My measuring device is between these two external points. We'll come back to our tests. Oh, you know what? I didn't close this down just for some peace of mind. Let me make sure it plays better when I'm not on camera. So I do see a question in the chat that I'll get to once this video is done playing. All right, so we're doing patient auxiliary now, right? Still using the same fault conditions. So we'll do normal conditions, or NC as the standard calls out, and we'll do a single fault condition on the second step. But I'm fading myself. What do I have to do? I have to change my probe configurations to probe high, probe low, because I'm now testing on two external points. Okay. Do that to both steps. Go back, save your files. Now let's go back to our first step, run the test, and still remember to turn on your DUT. All right, so what are we getting here? Again, we seem to always be getting 0.1 microamp when ground is closed because I'm bypassing the measuring device. So I'm not expecting much current. We'll let that run. And now I'm getting about 0.8 microamps. So the insulation between these two patient connectors, or the SIP-SOP, it's quality insulation because I'm not getting much current breaking through. Now again, ground is open, so I'm expecting a higher value. So if anything, when you're running your tests, that's a principle that you should be abiding by. Or if somehow your ground closed, or you're seeing the same leakage values when ground is open and closed, that can be a red flag. You know, you want to double check your connections. You want to make sure that when ground is open, you should be getting higher values when the ground is closed. I mean, that's not to say it's all the time. You know, maybe your insulation is tip-top and nothing leaks through, so that's definitely another scenario. So again, DUT is on, and we've passed. Awesome. Let's go back to our slides here. Or I'm sorry, Allison did have a question. I think, so we received a question about receiving extra training / certification. Can you talk about that quickly? Sure. Well, first and foremost, I want to say that I'm part of the application teams here at AR. All right, we have 3 application engineers and an overqualified intern. So that's our jobs. We want to make sure if you have any questions, if you are skeptical, if you're properly running these tests, we can quickly get on a phone call, we can get on a webinar like this, and depending on the situation, we sometimes fly out to locations. That gets a little bit more into the consulting side of things, but if you're looking to get training and certified, we do offer that. We do have consulting where we'll examine your specific DUT, identify what tests need to be ran, and we'll make sure all of your operators are trained on what's going on, how to run the equipment, and even understand the theory behind it. So you're not just looking at numbers and assuming it's correct because nothing's changed from yesterday, right? So feel free to reach out to Syed or Allison, but I don't want to be a salesman too much. I want you guys to feel comfortable reaching out to application engineers for those small questions. You know, that's what we're here for. We want to make sure we don't just ship you an instrument and wish you good luck. You know, we want to, these tests you're running are really important, not just to the success of your company, but the safety of the consumer. So you can always reach out to me at anthony.arroyo, ARROYO, at arisafety.com, or Allison can throw out our application email or Syed's email, or feel free to call us or reach out to us. All that information will be presented at the end of our webinar. But no, that's a good question. We've had this month alone, or maybe next month, we've had a few consultations where we've flown out to company company sites, and they're completely testing wrong, you know, and there's a lot of liability involved in testing wrong and sending out products that you're not 100% sure you've tested correctly. So to to mitigate that risk, if you don't mitigate, you will litigate, but to mitigate that risk, you know, it's definitely a good option to have you know, quote-unquote experts come out and give you some peace of mind. So now we get to mains unapplied part. This probably, people lose sleep over this test because it can be pretty complicated to set up, especially if you're trying to automate it. So we've completely introduced something new to this diagram. I now have this T2. This is this T2. I know what my T1 is, right? We still remember my T1 is my input power for my MD. Now, one of those fault conditions that we haven't talked about yet is introducing line voltage to one of your applied parts. It's a crazy fault condition, but what would happen if line voltage was somehow applied to your applied part? So now that's at a high reference and everything around it is at a lower reference. Is a ton of current going to leak? You know, so you do need, on top of your, let's see, okay, I see Allison has sent out that email. Thank you, Allison. So on top of your transformer internally that's powering up your DUT, that's not going to work for T2. You're going to need to buy a separate source, an APT source, to simulate, or to, I'm sorry, not simulate, but provide that T2 power. And what a lot of people miss out is you also have to reverse that polarity. You can see on T2 here, it's giving you that S9 switch, which is not only provide the line side to your applied part, but now throw the neutral at it too. And let's see what that current does. So you can see, let's read this. I feel like now that we've gone through all those diagrams, we can kind of understand what's happening here, right? Here's my MD, and here's the two sides of my MD. Now, the standard calls out to put a current limiting resistor in line with your MD, which is fine. In the video, I'm going to show you with how this works. I didn't do that, but for our purposes, you know, we don't need it. So one side of my MD is to either the high or low side of T2. So how are you even going to do that? You somehow have to isolate your line, neutral, and ground of your T2. You just can't have a three-prong plug and, you know, hold it to your measuring device. I mean, I guess you could, but it's not very safe. And you're going to have someone disconnecting it and reconnecting it on live parts. That's not what you want to do. And the other side of your MD is still on that applied patient part. Okay? So how would we do this in real life? Wow, we're running low on time, so let's get to this video. MOAP, as we call it, mains on applied part. So let's open this with QuickTime again. Let me turn off my camera. So I'm just going to go over the setup here. I'm not even going to run a test because we've seen what we see current readings, right? That's what we see. Oh wow, I'm sorry. This is probably not the best video right now. But let's roll with it. So we have, I think if I open this up all the way, it's just too big. View. Let's ask for some patience while all right, let's roll with this. So what have I added here? I've added an APT source in the middle here, if you can see it. Okay, and I still have my probe high, probe low here. We'll get to where that's connected in a second. So this black cord here is the output of my APT source, right? So I have that going, let me go back a second. I have that going to three exposed wires. I have my line exposed, I have my neutral exposed, and I have my ground exposed. And I've attached an alligator clip to each of those isolated lines. Because, again, as we looked at the diagram, I'm only sending one of those to my measuring device. So those alligator clips, I got them going to three distinctive channels on my scanner, right? And if you look on the far right side of that scanner, I have my probe low. So now I can short two of these. I can short my line with my probe low, have my neutral ground shorted, or reverse polarity, my neutral and my probe low, and line and ground shorted. So that's how you achieve that. And the other side of your MD, do you remember what that was? That was your applied part. So I still have that probe high going straight to the applied part medical device. So it's not that complicated if you know what you're doing. Yeah, that's easy to say, right? Nothing's complicated if you know what you're doing, but if you have a scanner, you can automate this test. Set your scanner channels and have a hit test ready system set up. Now I know a lot of people don't have that, and ideally that's what we would want to have. So let's go to the second poll question. I want to know, are you satisfied with your current leakage test setup? Do you wish it was animated? That'd be awesome. Automated? Do you feel there is room for higher efficiency? You know, most people aren't asking us for our consulting services unless they're getting an automated system where they can just hit test and all these tests run sequentially. I'm talking about earth leakage, enclosure leakage, patient auxiliary leakage, applied part leakage, a mains unapplied part leakage. All of those can be done without moving your connections. You just need scanners, you need the test parameters appropriately set up, you need those scanner channels, probably most important, appropriately set up, and ideally you'd probably be using our software, AutoWare 3 software, which you can save your test files to a PC. If an operator accidentally edits something, you can flash that back on.
All right, Tony, we have our results in. We asked, are you satisfied with your current leakage test setup? 55% of people are very satisfied, 27% of people are somewhat satisfied, 9% of people think there's room for improvement, and 9% of people feel that they need to rethink how they're performing touch current tests. Thank you guys so much for participating.
Okay. Thanks for that feedback. You know, I would say everyone needs to rethink it maybe every year just to verify we're doing it safely, most efficiently, our operators are safe, especially because most people are probably running high pot and ground bond along with line leakage testing. Something that I haven't gotten to was we have this standards reference guide that we saw for 60601-1 earlier in our slides. That's kind of a cheat sheet that we've created for our customers that Allison can shoot out for everyone to kind of give you a basis of where to start if you're one of the 9 or 18% that thinks there's improvement or needs rethinking. So feel free to reach out to Allison for our standard reference guide for our presentation here, and she's also shot out a document, 6 ways to fully automate your electrical safety test system, which, hey, more power to everyone. We want to help people. You know, we're not trying to get in your pockets. If you can pass your audits on your own, do it. We're here to help. If you think maybe it's gotten a little bit over your head, you know, feel free to inquire about the consulting stuff. Again, appreciate everyone's feedback on that poll question. Now, we're not even close to done. There's additional testing considerations. Mains voltage on applied part, which we didn't fully run, internal voltage on signal in, signal out, and external voltage on metal accessible parts that is not PE. But figure 16, 17, and 18 in your 60601-1 standard. But that'll have to wait for another webinar. I appreciate everyone's patience on sticking to us. Feel free to contact us or Allison at allison.oba@arisafety.com. Check out our website for more information. Special thanks to our marketing department, Maggie for making our slides, Syed for answering all those questions, and our intern Carol for helping us in every way she could. Join us for our next webinar, Wednesday, September 14th. Automate your production line, 6 ways to fully automate your electrical safety testing. There you go. You can have a webinar instead of reading through that document. So this is Anthony again. Thank you for participating. I'm sorry we started off late, and we hope you join us for our next webinar. Okay, take care.